Hi, and welcome to the additional content material for Week 1 of the Conquest of Space course. After this first week, you should now have an idea of how difficult access to space is. Before the formal notion of rockets, however, Tchaikovsky, one of the founding fathers of rocketry, introduced a more extravagant idea. Inspired by the view of the Eiffel Tower in 1885, 10 years prior to developing his famous rocket equation, which you will see more of in Week 2, Tchaikovsky dreamed of a structure which could reach geostationary orbit as a way of accessing space from Earth. Okay, so first, let's take a step back. What is geostationary orbit? Well, it is an Earth orbit at which a stable orbital speed is equal to the speed of Earth's rotation around its axis. That means that anything held in that orbit appears to be hanging always in the same position in the sky. If we could build a structure reaching up to this orbit and then climb it, we would effectively be in orbit around the Earth. What's the catch? Geostationary orbit is 36,000 kilometers above the equator. That's the equivalent of 120,000 Eiffel Towers. Tchaikovsky probably didn't put too much thought into it because in real life, no known material has enough strength to hold the weight of a structure of these dimensions. However, the idea is actually pretty interesting. By 1959, another Russian scientist, Yuri Artutanov, was publicizing the idea of building a structure held under tension by a counterweight, kind of like an upside-down plumb bob. This structure would be called a space elevator, and it would be the first time for this concept to enter the realm of feasibility. The idea for a space elevator then became part of the public interest, thanks to science fiction writer Arthur C. Clarke in his 1979 novel Fountains of Paradise. And, well, people have been looking into building one ever since. Let's look very quickly at the physics of the space elevator. So first, we have the cable, called the tether. It's linked to a counterweight which needs to go even further than geostationary orbit. One of the first serious studies proposed an altitude of 54,000 kilometers. The tether is held in place by opposing forces, gravity and the centrifugal force, which makes it stress under tension. This is key to the concept, as most materials are able to work with higher loads when under tension. The center of mass is located precisely at geostationary orbit. A climber, much like a typical elevator, then goes up and down the tether, delivering payloads to orbit. Below geostationary orbit, the climber must be powered, as the gravitational force is higher than the centrifugal force. However, because of the way the forces on the tether work, the space elevator also has an additional use. As the centrifugal force is higher than the gravity force once the climber is past the geostationary point, we could, in theory, accelerate a payload up to escape velocity from Earth's gravity for free. So if a space elevator makes so much sense, why haven't we built one yet? Well, it turns out that because Earth's gravity is pretty high, the strength of the materials needed for the tether is still out of our technological reach. But not by far. In the year 2000, carbon nanotubes were first manufactured, followed by diamond nanothreads in the year 2014. The tensile strength of these materials is currently between 20 and 50 times that of steel cables. And if they reached their theoretical limit of 100 times, these materials could actually make the elevator feasible. For now, however, we haven't been able to manufacture more than 1 meter filaments, so we're still quite far off from reaching the 36,000 kilometer or more needed for the tether. It seems like we have a while to wait for a space elevator here on Earth, but is there anywhere else we could build it? It turns out that there are pretty good candidates elsewhere in our solar system. Mars and the Moon, for example. In Mars, specifically, because of the reduced gravity and similar rotation speed to the Earth's, the elevator could be built using current Kevlar materials and a much smaller tether. Still, a lot of the engineering challenges remain. How do we actually build it? How do we avoid impacts with readily orbiting satellites or meteorites? What should we use as a counterweight? And who will pay for it? Some companies like Google or the Japanese Obayashi Construction Company have already started looking seriously into the matter. What do you think are the answers to these questions, and are there any other technological challenges you foresee in the construction of the elevator? What opportunities would it open for humanity? or forum is open for discussion.